this current module, we will discuss the lag models. These models are used to capture the dynamic nature of the economy. In this module, we will learn different terminologies in connection with lag models, for instance, the finite lag models or the infinite lag models. We will also look at different approaches in which we can write these different lag models so that we can estimate the parameters. In this module, we will discuss lag models. Since this is an introductory module, I will first explain a couple of examples. These examples will tell us what the scenarios are when we need to use a lag model. Let us look at the following example. Suppose a person receives a salary increase of $2,000 in his annual pay. Let us assume also that this increase is permanent, that is, the annual increase in salary is maintained. So how will this change in the person's annual consumption expenditure? Usually, if there is such an increase in the annual pay, the person does not immediately spend all the money. Suppose in the first year, he increases his consumption expenditure by $800, by another $600 in the next year, and by another $400 in the following year. Thus, by the end of third year, the increase in consumption expenditure is $1,800. So as we can see that the immediate increase of $2,000 in his annual pay did not annually increase his consumption expenditure by the same amount. The second example here can be considered as when income tax is increased. Consumers in this case have less disposable income, which again reduces their expenditure on goods and services, which in turn reduces profits of suppliers, which again reduces the demand for productive inputs and so on. But these effects are not instantaneous. The change in the income tax is not felt immediately but over a future time period. It is rather distributed over a future time period from when it has actually increased. Let us consider the first example that we have just discussed. Let us write the consumption function for this example as follows. Yt equals constant plus 0.4 xt plus 0.3 xt minus 1 plus 0.2 xt minus 2 plus ut. Models like these are called dynamic because they describe the evolving economy and its reactions over time. As we can see here, Yt, which has been influenced by xt, xt minus 1 and xt minus 2, where t, t minus 1 and t minus 2 represent the current time, 1 year before that and 2 years before that respectively. The above model shows that the increase in income of $2,000 is spread out over a period of 3 years. This model is thus called a distributed lag model. As we can see that the independent variables here are xt, xt minus 1 and xt minus 2, where t minus 1 and t minus 2 are the lag in time, and it has been distributed over a period of 3 years. So more generally, we can write a distributed lag model as follows. Yt equals alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 all the way up to beta k xt minus k plus ut. The above is called a distributed lag model with a finite lag. In the previous slide, we have seen a finite distributed lag model where the lag period was k equals 2. This model is a generalized distributed lag model which is for finite lag of k time period. In case of a finite lag model, we assume that the effect of a change in our independent variable x affects economic outcomes in y only for a certain fixed period of time. In our case, it is k. On the contrary, if we have an infinite lag model, then infinite lag models portray the effects as lasting essentially forever. In the above model, if you look, Beta 0 is called the short run or the impact multiplier because it reflects the change in the mean value of our dependent variable or our economic outcome y for a unit change in x for the same time period. In the previous model, beta 0 is called the short run or impact multiplier. If this change in our independent variable x is maintained at the same level, then the sum of the first two parameters beta 0 plus beta 1 will now reflect the change in the mean value of y in the next period, and beta 0 plus beta 1 plus beta 2 is the change in the mean value of y for the following period, and so on. The above sums of the regression coefficients are called interim or immediate multiplier. In general, if we go up to the kth time period, then the interim or intermediate multiplier is given by sum over I equals 1 to k beta I, which equals beta 0 plus beta 1 plus all the way up to beta k. And let us denote this summation as simply beta. Now, based on the above interpretation of the regression coefficients or the above expressions for the regression coefficients, let us define another parameter called beta I star, which we will define as the ratio of beta I, which is the ith regression coefficient, divided by summation I equals 1 to k beta I, where the denominator has previously been named as beta. So beta I star can be written as the ratio of beta I divided by beta. And the above expression here is called a standardized beta I or a standardized ith regression coefficient. The partial sums of the standardized beta i's will then give us the proportion of the long run or the total impact felt by a certain time period. So if we now go back to the consumption expenditure example, which was the first example that we had discussed, we can see that numerically the short run multiplier is 0.40 and the long run multiplier is 0.3 plus 0.2, which is a sum total of 0.9. And this is nothing but the sum of the estimates of the three parameters beta 0, beta 1 and beta 2. What the above estimates of the parameters mean are that for a $1 increase in income, the consumer will increase the consumption by 40 cents in the first year, 30 cents in the next year and 20 cents in the third year. The long run multiplier is hence 0.9. Now, if we divide each bi by 0.9, we obtain 0.44, which is beta 0 divided by sum of the betas. We have 0.33, which is beta 1 divided by sum of the betas, and 0.23, which is the beta 2 divided by the sum of the betas, which indicate that 44% of the total impact of a unit change in x is felt in the same time period. Now, what are the reasons for the lags? There are several different reasons why these lags in time period happen. One of these reasons are the psychological reasons. Now, force of habit stops people from changing consumption pattern immediately. For example, instant millionaires. When people win a lottery or through some other source win a lot of money, then they immediately do not change their consumption pattern. The reason is because they didn't have the extra money before, they had a particular expenditure pattern which they were used to. So once they have a lot of money, all of a sudden they don't start spending the money at the same rate at which they had acquired it. Also, people don't know whether the change is permanent or transitory. If transitory, then people tend to save up the current gain. This is another real situation which might happen when somebody comes into a lot of money suddenly. Because the person is not sure whether this increased source of income is a permanent one or not, He would want to save up whatever money he has immediately acquired. So these are some of the psychological reasons why there is a lag. The second reason for lag is technological reasons. Now, if the price of capital relative to labor declines, then making substitution of capital with labor is feasible for a firm. But if the firms believe that this decline in price is not temporary, then they do not rush to exchange their capital for labor. They would rather wait for some time to see if the change is permanent or not. This again gives rise to lags. And the third reason which might give rise to lag type of data is for institutional reasons. Let us look at an example. Contractual obligations stop the firms from switching from one source of labor or raw material to another. Those who have already placed funds in long-term savings account for fixed duration, such as 1 year, 3 years, or 7 years, are effectively locked in for that period of time, even though the money market condition may be such that higher yields are available outside. Another scenario is when employers give their employees a set of choice among several health insurance plans. But once the employees choose one particular plan out of the whole list, then they have to stick to this plan for at least a year before they can make a change. So here in this example, we can see that the employees are locked in for at least 1 year with the health insurance plan that they had chosen. Now, in case of data where there is a lag which can be noticed, we would like to model them with a pertinent lag distributed model. In case of a model, we have several parameters that define it, and since these parameters are unknown, we would like to estimate them. So in the next few slides, we will discuss the estimation of the parameters involved in a distributed lag model. Suppose our distributed lag model looks somewhat like the following expression. T equals alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus dot 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 plus yt. We have used dots because we do not know how far back into the past we would want to go. Such a model is called an infinite lag model, whereas the model that we have earlier discussed is called a finite lag model. Now, how do we estimate the coefficients of a distributed lag model? There are two broad approaches that we can use. These two approaches are a couple of more important or more readily used estimation methods for estimating the coefficients of a distributed lag model. The first method is called the ad hoc estimation, and the second is a priori restrictions on the betas, assuming the betas follow some systematic pattern. So let us first look at the first method of estimating coefficients of a distributed lag model. In an ad hoc estimation of distributed lag model, the explanatory variable xt are considered non-stochastic and they are assumed to be uncorrelated with the error terms. So xt minus 1 and xt minus 2 are also non-stochastic. Thus, the method of OLS works perfectly well in estimating the regression coefficient. It is suggested that the method of OLS be used but sequentially to get the estimates in a lag model. So first we regress our yt, which is the dependent variable, on xt, which is the value of the independent variable at the current time point. We then regress yt on xt and xt minus 1, where xt minus 1 is the value of the independent variable with a lag of one time period. And we then regress yt on xt, xt minus 1 and xt minus 2. And we carry on the regression process sequentially, adding one more value of independent variable at the next lag time period. This method of regression is continued until the lagged variables start becoming statistically significant, and/or the coefficient of at least one of the variable changes signs from positive and negative and vice versa. In other words, we sequentially regress our dependent variable yt on xt, xt minus 1, xt minus 2 and so on until and unless the coefficients corresponding to any one of the lag time period independent variable becomes statistically insignificant or the corresponding p-value becomes greater than the level of significance. Now there are certain drawbacks of this ad hoc method of estimation. Although the ad hoc method of estimation is quite simple to use, there are a number of loopholes. First of all, there is no a priori knowledge as to what should be the maximum length of lag. We do not fix a length of lag before we start fitting regression models to our data. Then, as we are performing estimation sequentially, there are fewer degrees of freedom left, which makes statistical inference or testing of the hypothesis, in other words, somewhat unreliable. The third drawback is that since we are considering successive values more often than not in economics, such values or such lags tend to be highly correlated. Thus, multicollinearity makes an appearance. Now, if the reader remembers, in one of the modules we had discussed the problems with multicollinearity. When we have several independent variables in a regression model that are highly correlated to one another, that is when the problem of multicollinearity creeps in. And in such cases, the estimation of the regression coefficients are no longer reliable, neither is the testing of the statistical significance of these regression parameters. So multicollinearity is one of the major problems which we need to take care of when fitting a linear model. Hence, multicollinearity being one of the challenges of this ad hoc method, it is a serious drawback of using this method of estimating the parameters. Now next, let us look at the Coyote approach to distributed lag models. Now, according to the Coyote's method of estimation of distributed lag models, we first assume the infinite lag model. This is the first and foremost assumption that we make when we use the Coyote approach to a distributed lag model. Now, according to Coyote's method of estimation of distributed lag model, since we assume an infinite lag model, we also assume that all the betas or all the regression coefficients are of the same sign. Coyote believes that the decline in the value of our regression coefficient is geometric, and it can be written as the following expression: beta k equals beta 0 times lambda raised to the power of k, where lambda is such that lambda lies between 0 and 1, and lambda is known as the rate of decline of the lag, and 1 minus lambda is known as the speed of adjustment. Now, using the expression beta k equals beta 0 times lambda raised to the power of k, we can write our regression model as yt equals alpha equals beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus dot 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 all the way to ut. Here in this expression, if we replace each of beta 1, beta 2, beta 3 and so on by beta 0 raised to the power times lambda raised to the power of k, we can write the same model as yt equals alpha plus beta 0 times xt plus lambda xt minus 1 plus lambda square xt minus 2 plus ut, which is the error term. If we number this current model as model number 1, then model number 1 is called the geometric lag model. In model 1, the effect of 1 unit change in xt minus I on the expected value of yt is given by delta expected value of yt divided by delta xt minus I, which equals beta I. This is nothing but the ith regression coefficient. We know from the interpretation of regression coefficient that the ith regression coefficient is nothing but the amount of change in yt for a unit change in the corresponding xt minus I. According to the Coic approach, we have written bk equals b0 times lambda raised to the power of k. So here we can write beta I equals beta 0 times lambda raised to the power of I. This expression tells us that the change in average value of y or expected value of y in period time t given a change in x in period t minus I, all other factors kept constant, is given by beta I, which equals beta 0 times lambda raised to the power of I. If this change is sustained permanently, then the long run multiplier will be given by the sum of the estimates of beta, as we have seen before. So if we write the sum of these betas, beta 1, beta 2, beta 3 and so on, and replace them with the expression beta 0 times lambda raised to the power of k, then we have beta multiplied by 1 plus lambda square plus lambda 3 plus dot dot dot. And this is nothing but a geometric series which will give us the expression beta naught divided by 1 minus lambda. And because of this reason, the above model, model number 1, is called a geometric lag model. Now in the Coic approach to distributed lag model, since lambda is less than 1, each successive beta is numerically less than the previous one. We have seen that beta k equals beta 0 multiplied by lambda raised to the power of k. Since lambda is less than 1 or a fraction, so taking a power of that is reducing it further and multiplying it with beta 0 will give us numerically less than the previous beta that we had received. The implication of this is hence quite clear. The effect of lag on yt becomes progressively smaller and smaller. So as the value of lambda gets closer to 1, the slower the rate of decline, thus the distant past values of y will have a sizable impact on yt. Whereas the closer lambda is to 0, the more rapid the decline and the influence of x on yt dies out quickly. In other words, when we have data values for the independent variable in the near past, then x has a sizable impact on yt. However, if we take the values of independent variable in quite far away from the current time, then the influence of x on yt dies out very quickly. Now let us discuss some of the features of the Coic scheme or the Coic approach. Because of the non-negativity assumption of lambda, we had seen previously that lambda lies in between 1 and 0. Coic rules out the chances of betas changing signs, and this is why this was one of the assumptions made in the Coic approach. One of them was the model that we considered was an infinite lag model, and the second assumption was that the betas or the regression coefficients did not change signs. And here we see the reason why, because of the non-negativity assumption of lambda. Now the assumption of lambda less than 1 gives lesser weight to the distant betas, as we had seen in the previous slide. As we go further away back in time, the effect of the values of the independent variable x gets lesser and lesser on our dependent variable y. So hence we ensure that the sum of all the beta coefficients, which is the long run multiplier, is given by summation k equals 0 to infinity beta k, which can be again written as in terms of beta 0 and lambdas as summation k equals 0 to infinity beta 0 times lambda raised to the power of k. So beta 0 being independent of k can be taken out of the summation. So we have beta 0 multiplied by summation k equals 0 to infinity times lambda raised to the power of k, and this is nothing but the sum of a GP series or a geometric progression series. So this gives us beta 0 times 1 divided by 1 minus lambda, and this is finite. Now according to the Coic approach, we can write the infinite distributed lag model in terms of alpha, and in place of beta 1, beta 2, beta 3 and so on, we can replace them by beta 0 multiplied by lambda raised to the power of k. in this model, as you can see, also contains a large number of parameters. In fact, if we look at this model, there are an infinite number of parameters since we kept an open end on the time period or the lag in the time period that we wish to go back in time. So we have beta, 0 and an infinite number of lambdas, and also in this model we have multiplied terms of beta 0 and lambda together, which makes the model non-linear. So because this model is non-linear and it has a high number of parameters, the method of linear regression analysis is not usually applicable to such a model. So since, if the reader can recall, the model which we had numbered as 1, if we write that model, which is the infinite lag model, as yt equals alpha plus beta 0 xt plus beta 1 xt minus 1 and so on plus ut, in this model we have infinite number of parameters in the form of alpha, beta 0, beta 1, beta 2 and so on. Again, if we write this model using the Coic transformation, we now have alpha plus beta 0 xt plus beta 0 times lambda xt minus 1 plus beta 0 lambda square times xt minus 2 plus so on plus ut. Again, in this model we have beta 0 and lambda in the nonlinear form. Because of these two constraints, Coic came up with the transformation, which is as follows. So first he takes lags by one period time to obtain yt minus 1 equals alpha plus beta 0 xt minus 1 plus beta 0 lambda xt minus 2 plus beta 0 lambda square xt minus 3 and so on plus ut minus 1. He then multiplies the above equation by lambda and we get the following expression. Lambda multiplied by yt minus 1 equals lambda alpha plus lambda times beta 0 xt minus 1 plus beta 0 lambda square xt minus 2 plus beta 0 lambda 3 x lambda cube xt minus 3 plus so on plus lambda times ut minus 1. Next, by subtracting the models for yt and yt minus 1, we now have yt minus lambda times yt minus 1 equals 1 minus lambda times alpha plus beta 0 xt plus ut minus lambda times ut minus 1. Or if we rearrange the terms by keeping just yt on the left hand side, we now have yt equals 1 minus lambda times alpha plus beta 0 xt plus lambda times yt minus 1 plus vt, where vt is a moving average of ut plus ut minus 1. In other words, vt equals ut minus lambda times ut minus 1. The procedure that we have described above, all the steps included, they are called the Coic transformation. So in the earlier infinite lag model, we had infinitely many parameters and alpha that had to be estimated. But the Coic transformation of beta k equals beta naught times lambda raised to the power of k has reduced the number of parameters to just 3, that is alpha, beta 0 and lambda. Some features of the Coic transformation are as follows. Starting with a distributed lag model, we end up with an autoregressive model. We had seen in the previous model that if we go through the different steps of Coic transformation, what we ultimately get is a model that is written in terms of xt, xt minus 1 and yt minus 1. These are the variables on the right hand side and they write the model which we use to model our yt. So since we have yt minus 1 involved in the model used to predict yt, we now call it an autoregressive model. The classical least square theory assumes that the explanatory variables are all non-stochastic. Hence, we must find out if yt minus 1 satisfies this condition. As we have seen in the model that yt minus 1 is one of the variables that we use on the right hand side of the model to predict yt. Hence, we must also find out if yt satisfies the condition of non-stochasticity. The third feature of the correct transformation is that the error term in the new model is now Vt and not Ut. If you remember, the new error term Vt is the moving average of Ut and Ut minus 1. Vt equals Ut minus lambda times Ut minus 1. The statistical property of Vt depends again on the properties of Ut. Hence, if we have correlated Uts or error terms, we will have a serially correlated Vt. Thus, we have to deal with a serial correlation problem among the error terms, which is undesirable. Also, the presence of Yt minus 1 as one of the explanatory variable violates the assumptions that underlie the Durbin-Watson test of autocorrelation. Thus, we will have to look for an alternative to the Durbin-Watson D test. Now, this is all in this module. We will discuss further the estimation of parameters in a lag model setup and also the Durbin-Watson, an alternative for the Durbin-Watson D test in the next module. In this module, we have discussed some examples, and under these scenarios, we fit a lag distributed model to our dataset. We have seen how we can develop such a model or why we wish to develop such a model. We have also learned some of the terminologies like distributed lag or why we have distributed lag. We have looked at different types of reasons which gives rise to these lag models like psychological reasons, institutional reasons, and so on. And we have also discussed the Koyok approach. This is a very new approach and it is a very commonly used one in these days. This approach helps us write the lag model in a different form which helps us estimate the parameters by reducing the number of parameters that we have in the model. There are a number of discussions about the estimation of the parameters in a lag model, but we will dedicate a separate module to their study.